This is a satellite foundational course for GOES-R on multi-channel interpretation approaches for use with the ABI. It includes information on band differences, why they work, and what information they show, which band differences are in AWIPs, and on RGBs, red, green, blue composites, including the baseline RGB products in AWIPs. The topics of this training are related. There are different ways of looking at channel differences from the GOES-R Advanced Baseline Imager, or ABI. You can look at difference fields, that would be brightness temperature difference for infrared or reflectance difference for visible or near infrared. You can toggle between fields, and you can look at RGBs, or red, green, blue images. RGBs are created by assigning an individual band or band difference to the three color components, red, green, and blue, that are used to create an image. All of the ways of looking at channel differences highlight the sensitivities of the individual channels. This chart lists the bands that are available on the GOES-R Advanced Baseline Imager, or ABI. The chart shows 16 bands, the central wavelength, the wavelength range, the resolution, and the band nickname. The nickname gives you an idea of what the band can be used for, but there are lots of other possibilities that extend beyond the nickname. Band placement is typically related to absorption by a particular gas, be it water vapor, sulfur dioxide, ozone, or carbon dioxide, or bands are placed in a region where there is little absorption by atmospheric gases. There are satellite foundation course trainings on the individual bands. Check them out. When you're looking at band differences, or at RGBs, or even just comparing one band to another, it's important that you understand the physics of the band in question. Why is that particular band included on ABI? There are training modules on individual bands to which you can refer. When band differences are considered, what differences between the bands exist and why? Some of those are listed on this slide and will be considered more in depth in this training. Some brightness temperature difference fields are very well known. These are listed below. That they are well known in part underscores why the channels are included on ABI. There are pre-computed channel differences in AWIPs. Many of these are also components of RGBs. The split window difference, for example, detects moisture or dust in the atmosphere. Split cloud top phase can be used to ascertain cirrus thickness. Night fog and day fog highlight low stratus clouds. Other channel differences here do have well-defined uses. The physical reason that the channel differences give information is listed here. This chart that you've probably seen before shows the infrared channels on ABI. The blue regions show where individual bands are detecting energy. Some are narrow, band 10, and some are relatively wide, band 8. The red line can be interpreted in two ways. Either the relative amount of absorption by any gas in the atmosphere, or the brightness temperature sensed by the satellite in clear skies above a U.S. standard atmosphere. Cooler brightness temperatures result when absorption by a gas occurs in the atmosphere. Strong absorption by water vapor is apparent in bands 8, 9, and 10. Ozone absorption is apparent in band 12, and CO2 absorption occurs in band 16. These bands will all give cooler brightness temperatures in clear skies than in window channels like band 7 or 13. When the red line is near the bottom of the chart, little absorption is occurring at that wavelength. This is the case for the 10.3 micrometer band 13. Many of the heritage difference products use 10.7 micrometers on GOES 13, 14, and 15. How does that particular channel compare to the closest ABI channels, 13 at 10.3 micrometers and 14 at 11.2 micrometers? The 10.3 micrometer channel on ABI is cleaner. That is, there is less water vapor absorption, and it's narrower than the 10.7 micrometer channel on GOES 13, 14, and 15. The 11.2 micrometer channel is also narrower than the 10.7 micrometer channel, but it has similar amounts of water vapor absorption. If you want to highlight water vapor differences between channels with a split window difference that includes a 12.3 micrometer channel, maybe 10.3 micrometer is the channel to use, but 11.2 micrometers will give similar results. The split window difference is very sensitive to changes in skin temperature, so be careful in interpreting it, especially with regard to temporal changes. But in this case over Kansas from June 2017, the split window difference is highlighting a tongue of moisture in clear skies. Moisture is concentrated in a small region. This is where you might expect convection to develop, where moisture is most plentiful. And 3 hours later, strong convection that would later produce significant hail has developed along the axis of moisture. Note that the split window difference field values here have increased in general, because the skin temperature has increased. Gradients remain in place, however. The split window difference also detects dust. When energy radiates upward from the surface through a dust layer, the amount of absorption and subsequent re-emission varies with wavelength. In particular, dust is a good absorber of 10.3 micrometer radiation, but not so for 12 micrometer radiation. 10.3 micrometer energy leaves the warm surface and is absorbed by dust higher in the atmosphere, and then re-emitted from that higher level where the temperature is cooler. 12 micrometer energy leaves the warm surface and passes through the dust without being absorbed as much, so there is less re-emission from the colder higher levels. Thus, the 10.3 micrometer brightness temperature will be cooler than the brightness temperature at 12 micrometers. It's common for dust RGBs to include the split window difference as one of the colors. Now, it is true that water vapor in the atmosphere will more readily absorb the 12 micrometer energy, the reason why the split window difference can detect moisture distributions. But this is a dust storm. It's occurring in a region without a lot of water vapor present. The dust absorptive differences for the 10.3 and 12.3 micrometer channels are mirrored in the ice absorptive differences in the 11.2 and 8.4 micrometer channels. Again, why does greater absorption lead to cooler brightness temperatures? Much of the 11 micrometer energy upwelling through, in this case, an ice cloud will be absorbed and then re-emitted from the colder temperature. Proportionally, not as much energy at 8.4 micrometers is absorbed. If there isn't absorption, or if there is less absorption, the emitting surface is farther down, closer to the surface, in the warmer atmosphere. In this example of convection off the South Carolina coast, thin cirrus, as inferred also perhaps by the inset 1.38 micrometer imagery, shows as magenta and white, whereas thicker cirrus is blue. This is because more low-level 8.4 micrometer energy is upwelling through the thin cirrus. 11.2 micrometer energy that's upwelling is more likely to be absorbed. There are also subpixel effects that must be considered in any brightness temperature difference field. There isn't really a subpixel effect in clear fields of view or in completely cloudy fields of view, but there is a big impact on partially clear fields of view. When a cloud does not completely fill a pixel, parts of the pixel will be filled with colder regions and parts will be filled with warmer regions. Shorter wavelength detectors are more sensitive to the warm regions, and longer wavelength detectors are more sensitive to the colder regions. And this subpixel effect leads to differences in computed brightness temperatures in the ABI bands that are independent of gas absorption. Several plots on this page document subpixel effects. 4 window channels are shown on the upper left, and you can see that detected temperatures cool for this thin cirrus as the wavelength of the observation increases. Longer wavelength detectors are more sensitive than shorter wavelength detectors to the colder parts of a pixel. That's the subpixel effect. The figure in the bottom left shows a shaded region from which points are extracted for the figures on the right. The bar graph shows the number of pixels showing a given temperature, colder to the left, warmer to the right. Note how shorter wavelengths show more points that are relatively warmer, and longer wavelengths show more points that are colder, as expected for the subpixel effect. The bottom right figure shows a density diagram of band 11, that's 8.6 microns on Himawari, versus bands 13, 14, and 15. The dashed line shows x equals y, and you can see that the temperatures observed at shorter wavelengths are typically warmer than those observed at longer wavelengths. Another well-known difference field is used to identify regions of low stratus and fog. Clouds made up of water droplets are not black body emitters of all wavelength radiation. Satellite detectors of radiation simply collect a number of photons. The conversion of those radiance counts to brightness temperature assumes black body emission, however, So if a surface hasn't emitted as a black body, meaning less photons than a theoretical maximum have been emitted, then the inferred temperature will be cooler. This occurs for 3.9 micrometer radiation, but not for radiation around 10.3 micrometers. For water-based clouds, that is clouds composed of water droplets, the 3.9 micrometer brightness temperature is cooler than the 10.3 micrometer brightness temperature at night, or the 10.7 micrometer brightness temperature on GOES 13, 14, and 15. In this cross-section from a fog bank to a cirrus deck, you see differences in the brightness temperature that are related to emissivity differences in the low stratus, so that the 3.9 micrometer brightness temperature is cooler than 10.7, and you see transmissivity differences in cirrus and subpixel effects, so that the 3.9 micrometer brightness temperatures are warmer than the 10.7 micrometer brightness temperatures. In clear regions at night, the 10.7 and 3.9 micrometer temperatures are similar. It's not only clouds that can affect 3.9 micrometer temperatures. This graph shows emissivity over water, pretty close to 1, dry sand, red clay, and tree leaf. Dry sand and red clay have emissivities that are much less than 1. Black body temperatures over this then will be cooler than black body temperatures computed at other wavelengths where emissivities are closer to 1, like at 11 micrometers. Keep this in mind when you're looking at brightness temperature differences that key off emissivity differences, like the night fog brightness temperature difference. Reflectance differences are what's important for visible and near-infrared channels, as shown on this chart showing the 2 visible and 4 near-infrared channels on ABI. Note, for example, how much more reflective grass is in the green in the 0.86 micrometer band 3, the veggie band, than in the 0.64 micrometer visible. Note how much more reflective snow ice are in the visible compared to the 1.6 micrometer channel. These differences can be played off one another to highlight features in either difference fields, or in RGBs, or in simple comparisons, that is visual inspection of the 2 bands. In band 3, the veggie band on ABI is at 0.86 micrometers, green vegetation is far more reflective than in the visible channel. Thus, this band excels in distinguishing between land and water. Bodies of water surrounded by land will really pop out, so it's great for examining changes due to excessive rainfall, that is flooding. Because green land is so reflective, clouds are sometimes hard to distinguish over land in the 0.86 micrometers. There's more contrast over land in the visible, in the 0.64 micrometers. Snow and ice clouds are highly reflective in the 0.64 micrometer visible band on ABI, but snow absorbs energy at 1.6 micrometers. Thus, snow and ice and clouds made up of water droplets that look similar in the visible 0.64 micrometer imagery will look much different in the 1.6 micrometer imagery. This figure of a wave cyclone in the western Atlantic shows a cirrus shield that is much less bright than the lower water clouds. That's because ice is absorbing a lot of energy at 1.6 micrometers and not reflecting it. There's also a band of snow on the ground over the mid-Atlantic states that shows up as dark. Let's now consider RGBs. To interpret RGBs, you must understand how colors are constructed in modern computer imagery. In the color cube shown, the primary colors, red, green, and blue, are at 3 corners of the cube. White, which is all colors, and black, no colors, are at 2 other corners. And the remaining 3 corners are color combinations. Yellow, which is red plus green with no blue. Cyan, which is green plus blue with no red. And magenta, which is red plus blue with no green. All colors can be found in the color cube based on the 3 color combination. For example, orange is a lot of red plus some green and no blue. Knowing how different colors are created will help your interpretation of RGB imagery. This slide shows how changing one of the 3 inputs will affect the RGB image. The columns show the red, green, and blue components and the derived RGB. The top line shows the red, green, and blue bands from Terra Modis and the true color RGB that's derived from them. The control, if you will. In the second line, the red component is only half as bright, but the green and the blue remain at full intensity. In the third line, the green component is half as bright, and the red and the blue are full intensity. And in the fourth line, the blue component is half as bright, and the red and the green are at full intensity. The RGBs from the 4 combinations are in the rightmost column. With less red, the RGB acquires a cyanish hue because blue plus green is cyan. With less green, the RGB acquires a purple hue because with less green you see more red and blue, which makes magenta. And with less blue, the RGB acquires a yellowish hue because with less blue you have red and green that makes yellow. In this example, my opinion is that the RGB with halved green is the most unnatural looking, perhaps indicating the importance of green wavelengths over a vegetated surface in a true color RGB. You can create single-banded combinations of RGBs using an online tool at the URL on the screen. Click on it. This web app uses current ABI data, allows you to choose single bands for the red, green, and blue components, and creates the RGB combination. In this way, you can explore the different possibilities combining single ABI channels. Here's a daytime image that combines 10.3 micrometers in the red, the visible 0.64 micrometers in the green, and the snow ice 1.6 micrometers in the blue. Do you have a guess what you'll see? What color will the hurricane in the Pacific be, for example? Were your guesses correct? Water clouds will be cyan without a lot of red, 10.3 micrometers, because they are warm. High ice clouds, like over the hurricane, are yellow because they don't contain a lot of blue from the snow ice channel. Here's the same RGB as produced in AWIPS. RGBs that are present in AWIPS have been changing at times in the past 18 months as of midsummer 2018, but they are now relatively stable. They're listed here. You can also find additional information on RGBs at the link to a comment module or to the link to UMetSat at the bottom of the page. There are 7 RGB images that you'll see next. Given the bands, maybe you can guess what you'll see and why you are seeing that color. But for some of the RGBs, that's far more difficult because 1, a band difference is used, and 2, only certain ranges of that band differences are included in the RGB. Note that if reflective channels are used, the product is generally not useful at night. In this first example, the fire temperature RGB, 3.9 micrometer data are used for the red component, 2.24 micrometer are used for the green, and 1.61 micrometer are used for the blue. As the fire gets hotter and hotter, red data, that is almost always there, is augmented by first green data, so red and green makes yellow, and then blue. So as a fire develops and increases in intensity, its color will change from red to yellow to white, as shorter and shorter wavelength energy is emitted by the hotter and hotter fire. Not all the dynamic range in the channels is used in the RGB. That's shown here. For the red channel, only temperatures between 0 to 60 Celsius are considered. For the green, reflectances of 0 to 100 are considered, and for the blue, reflectances of 0 to 75 are used. In addition, a gamma of 2.5 has been applied to the red. Gamma is a way to tweak how the component is presented. If gamma is greater than 1, then the high end of the distribution is highlighted, so in this image, the hottest pixels are emphasized. If gamma were less than 1, then the low end of the distribution would be highlighted. In this case, for the red, the cooler pixels would then be highlighted. Here's the same RGB, but with gamma equals 1 for the red. Features outside the fire become more apparent in the RGB when the red gamma is reduced. If gamma were made very small, then the fire would be hard to see at all in this RGB because all the contrast in the red would be focused at the cold end of the scale. The air mass RGB has a long history. It uses the split water vapor difference as its red component, the split ozone as green, and the upper level water vapor as the blue. Channel differences used in this RGB and in others are in AWIPS. For information on why the channel difference might be part of the RGB, consult the quick guides for those channel differences. The split water vapor values used for the red component range from 0.6 to minus 26.2. Split ozone values for the green range from 6.7 to minus 43.2. And water vapor values range from minus 64.7 to minus 29.3 for the blue component. Nighttime microphysics is another RGB with a long history of use. It uses the split window difference as its red component, the night fog brightness temperature difference as its green component, and the clean window channel, 10.3 micrometers, band 13, as its blue component. Quick guides for RGBs and AWIPs have been developed and are available in the AWIPs Interactive Resource and in VLab. Ranges for the components are 2.6 to minus 6.7 for red, 5.2 to minus 3.1 for green, and 19.5 to minus 29.5 for blue. Day Snow Fog combines the Veggie band, band 3 at 0.87 micrometers, the Snow Ice channel, band 5 at 1.61 micrometers, and the Day Fog brightness temperature difference, 3.9 minus 10.3. It's useful only during the day. Reflectance values for the 0.87 micrometer and 1.61 micrometer bands are 0 to 100. Brightness temperature difference values used are between 30 and 0. Additionally, a gamma of 0.59 is applied to all three components. This emphasizes the low end of the scales. Here's what the RGB looks like with gamma equal to 1 rather than 0.59. Dayland Cloud is another daytime-only RGB, using the 1.6 micrometers band in the red, the Veggie 0.87 micrometer band in the green, and the red visible 0.64 micrometer in the blue. This RGB is similar to one that is called natural color. It uses reflectance values between 0 and 97.5 in the red, between 0 and 108.6 in the green, and between 0 and 100 in the blue. SIMS Natural Color simulates true color imagery from ABI even though a green visible channel is not present on the satellite. It uses reflectance information in the Veggie band as a proxy for green. It is similar to a product like GeoColor shown in the inset, which is available via an LDM request, but has a simpler construct and requires less processing. So SIMS Natural Color uses the red visible in the red, and the blue visible in the blue, and the green is derived from the Veggie band. AWIPS includes gamma control to manipulate the look of RGBs under the Composite Options menu item in AWIPS. To access the control, right-click on the annotation label in the RGB image and then click on Composite Options. Gamma controls where the most contrast exists in the RGB. For smaller values, the darker part of a grayscaled image from dark, warm to light, cold shows more contrast, and for larger values, the brighter part of the image shows more contrast. The min-max values for each input can be adjusted as well as gamma. Here's the same image as the last slide, but with a gamma change from 0.6 to 0.2 for the green part of the RGB. The warmer part of the green, the low-level water vapor, is emphasized now and those features become more apparent and greener in the RGB. The 16 bands on ABI offer unprecedented geostationary observing capabilities. Each individual band can be used to observe phenomena, and band combinations or differences can highlight features or levels in the atmosphere. Furthermore, RGB imagery can further bring out information that is present in component bands. A good practice when interpreting difference fields, or RGBs, is to have the component pieces at hand. Fields in one can be better interpreted if you have the ability to interrogate fields in the originals. Here are some additional internet resources to browse. This includes quantitative products that are available. They nicely complement channel differences or RGB products that are more qualitative. Quick guides on channels, channel differences, RGBs, and baseline products are also available at the links and in VLab. This concludes the multi-channel interpretation part of the Satellite Foundational course for GOES-R. Thanks for listening.